Alright, so for review purposes, I'm going to go ahead and rederive the shape functions for a beam, although we could just write them down. Our beam is going to go from 0 to L. We'll plug in the 10 meters later. But if you remember, for a beam, we use Hermite interpolation. So we have x, the interpolation polynomial, evaluated at the first node, then minus the derivative of x with respect to x, evaluated at the first node. You guys remember that from beams? And then x evaluated at L, and minus the derivative of x with respect to x, evaluated at L. So there's our shape functions. All right. So then we can just start right in. The element stiffness matrix is from 0 to L. Not So this is actually no different than what it was previously, right? The stiffness matrix is exactly the same. So you guys have seen me do this before. So there's the stiffness matrix. It's exactly what it was before. So we could have just wrote it down. So then the element mass matrix. I'm actually just going to copy that part and then just change the integrand. All right, there's the mass matrix. So everybody okay to hear?
I have a quick question.
Go ahead.
So up there where you have the stiffness matrix, you don't have the derivatives of the shape function. I mean, on the screencast view, but on the board, it's just EI, Ni, and J.
For the stiffness matrix?
Yeah.
Oh, okay, yeah, that was a mistake.
That should be.
It should be the second derivative of. Yeah, that was just. It's actually in my. I don't know what I was doing because it's in my notes right here. I just miscopied it. But, you know, like I said, that's exactly the same stiffness matrix as we previously had for the beam. So, yeah, go ahead and correct that. Sorry. Good catch. All right. So we still have to apply. Now we're just have one element here. If we had multiple elements, we would do an assembly procedure just like we had before, except now we would assemble the mass matrix, but it'd be exactly the same as the stiffness matrix because they're the same size, right? So we'd assemble the mass matrix and assemble the stiffness matrix, and then we apply the boundary conditions. So here we only have one element. We're going to apply the boundary conditions. It's a cantilever beam, so at node 1, both the transverse deflection and the rotation will be 0. Okay. So we're going to do the drop thing that I've done. So I'm going to drop the first two. The first the mass and stiffness matrix are 4x4s, right? So the first two rows correspond to, and columns correspond to those 2 degrees of freedom. So I'm just going to drop those down. So I'll say K nu is equal to drop KE 1, 2, drop So I'll just drop in that and then do the exact same thing for the mass matrix. Okay, and I guess, I mean, now is just as good a time as any to apply the boundary conditions. So what I'll do is I'll say A is equal to inverse M nu times K nu, and then I'm going to plug in all those numbers. So AY 4.95, 10 to the minus third, IY 125, 10 to the minus sixth, and so then we can just find the eigenvalues of A, and there they are. Now, of course, that's the eigenvalues, lambda, which is omega squared. So if you really wanted to know what the natural frequencies of this particular beam are, then 28 hertz and 278 hertz. So that's the first two frequencies, okay, at least according to this analysis. It's going to get more accurate as you use more nodes and whatever. But we can also, in the same way, get the eigenvectors. So the command here is just eigenvectors. A. Okay. And then we can, just for fun, we can do something kind of neat with those, in that we can plot the solution. So we're going to say, you remember, we assume a solution U of H is equal to Uj Nj, right? The position of the nodes. Okay. Well, we can use the eigenvectors are representative of the deformation. And in particular, in Mathematica, these are unit vectors. So these are unit vectors of the degrees of freedom that correspond to the modes of deformation, the first two anyway. So what we could do is something like, I'm going to say 0, 0, because we zeroed out the first two nodes, okay? And then vec 1, 1, vec 1, 2. So just so you can see what that is, it's just that. And now I'm going to dot that into the shape functions. And if we plot this, it should give us a picture of what, well, I'll have to plug in about the value of L. Okay, so that is what one of the modes look like, in particular, the second mode. I know it's the second mode because the eigenvalues are sorted opposite. So this eigenvector corresponds to that eigenvalue, which is the second frequency. This eigenvector corresponds to that one, which is the first frequency. So let me stop this. I don't know what's going on. It's bugging me. And the plot looks funny, right? Because it's the aspect ratio is not correct. It's 10 long and less than a meter high. So we could fix that, though. We could say aspect ratio and it gives it a little bit better representation of what the deformation looks like. And then, just for fun, we could do something like this. And that would work if I'd fixed the plot range. So we go from 0 to 10, minus 1 to 1. So that's what the second mode would, how it would vibrate. And we could do the same thing for the first mode. The first mode is not, I guess, not as quite as fun because it's just what you'd expect, right? Like that reminds me of my son does it all the time. The thing that stops the door from hitting the wall, you know, that little thing you pluck and it vibrates. Okay.